What if I told you that everything we see, the stars, the galaxies, the vast stretches of cosmic emptiness, is being pushed apart by an invisible, mysterious force? A force so powerful, it's accelerating the expansion of the universe itself, yet remains almost entirely hidden from our understanding. This is dark energy, the universe's greatest enigma, an unseen hand sculpting the fate of everything that exists. And right now, we're living in the cosmic dark energy era, a time when this mysterious force dominates the cosmos, shaping its destiny in ways we're only beginning to grasp. Think about this for a moment. Nearly 70% of the universe is made up of dark energy, and yet we don't even know what it truly is. It doesn't emit light, it doesn't interact with matter the way anything else does, and its presence is only revealed through its cosmic fingerprints. The way galaxies drift apart faster and faster, as if space itself is stretching against the laws of physics we thought we knew. For centuries, we believed gravity would eventually slow the universe's expansion, pulling everything back together in a cosmic collapse. But dark energy flipped that script entirely. Instead of slowing down, the universe is speeding up, racing toward an unknown future, and we're left with more questions than answers. That's where this journey begins. Over the course of this exploration, we'll uncover 25 of the most baffling mysteries surrounding dark energy and the era it defines. From the mind-bending possibility that dark energy could tear the very fabric of reality apart, to the haunting question of whether it's connected to other cosmic puzzles like dark matter or the birth of the universe itself. Each mystery pulls us deeper into the unknown, challenging everything we think we know about space, time, and existence. So if you've ever looked up at the night sky and wondered what secrets lie beyond the stars, you're in the right place. Because this isn't just a story about the cosmos, it's a story about our quest to understand it, and the thrilling, sometimes unsettling truths we're uncovering along the way. The first mystery takes us back to the late 1990s, when astronomers made a discovery so shocking it upended our entire understanding of the cosmos. They were studying distant supernova exploding stars so bright they can outshine entire galaxies, expecting to confirm that the universe's expansion was slowing down under gravity's pull. But what they found was the opposite. These stellar explosions, billions of light years away, were fainter than they should have been, meaning they were farther away than expected. The universe wasn't just expanding, it was accelerating, as if some invisible force was pushing galaxies apart faster and faster. This revelation sent shockwaves through the scientific community. Einstein's equations had allowed for a cosmological constant, a kind of anti-gravity that could explain such behavior, but even he dismissed it as his greatest blunder when observations at the time suggested a static universe. Now, dark energy, a modern version of that very idea, has forced us to reconsider. Unlike gravity, which pulls matter together, dark energy seems to stretch space itself, creating more room between galaxies with every passing moment. But how do we measure something so elusive? One key lies in the Hubble constant, the rate at which the universe expands. By comparing the brightness of supernovae to their redshift, how much their light stretches as space expands, scientists can track changes in the expansion rate over cosmic time. The data paints a clear picture. Around 5 billion years ago, dark energy became dominant, overpowering gravity's grip and kicking the universe into high gear. Here's where it gets even stranger. If this acceleration continues unchecked, dark energy could lead to a future where distant galaxies vanish from view entirely, their light stretched beyond detection. The cosmos would grow cold, empty, and eerily silent, a fate known as the Big Freeze. But is dark energy truly constant, or could it change over time? Some theories suggest it might grow stronger, potentially tearing atoms apart in a catastrophic Big Rip. Others propose it could fade away, allowing gravity to reclaim control. Each possibility forces us to confront profound questions about the nature of reality itself. So while we've uncovered dark energy's fingerprints, its true identity remains hidden. Is it a property of space itself, a new kind of energy field, or something even more exotic? Every answer leads to deeper mysteries, reminding us that we're just beginning to unravel the secrets of this dark, accelerating era. If dark energy is the invisible force driving the universe apart, what exactly is it made of? That question lies at the heart of the second great mystery, and the answers scientists have proposed are as fascinating as they are unsettling. The leading theory points to something called the cosmological constant, a concept Einstein first introduced as a mathematical fix for his equations, only to later reject it. But here's the twist: modern observations suggest he might have been onto something after all. Imagine space itself as a vast, bubbling sea of energy, where even the emptiest vacuum isn't truly empty. According to this idea, dark energy is the relentless pressure of that vacuum, an unchanging force woven into the fabric of reality, gently but insistently pushing galaxies apart. The numbers almost fit, but there's one glaring problem. When physicists calculate how much energy the vacuum should contain, their predictions overshoot reality by a staggering margin, up to 120 orders of magnitude. That's like expecting a whisper and getting a supernova instead. This inconsistency has led researchers to explore even stranger possibilities like quintessence. Unlike the steady cosmological constant, quintessence is dynamic, a cosmic fluid that shifts and evolves over time. Picture it as a hidden tide, ebbing and flowing through the universe, sometimes weakening, sometimes strengthening. Some models suggest it could even interact with dark matter, the universe's other great enigma, creating a delicate dance between the forces shaping the cosmos. But so far, no telescope or experiment has caught a glimpse of quintessence in action. Then there's the most unsettling contender, phantom energy. This hypothetical form of dark energy wouldn't just accelerate the universe's expansion, it would grow more powerful as space stretches, eventually overcoming all other forces. The result, a catastrophic big rip, where galaxies, stars, planets, and even atoms are torn apart in a final, violent crescendo. The debate doesn't end there. Some theorists argue dark energy might not be an energy at all, but instead a sign that Einstein's theory of gravity breaks down on cosmic scales. Others propose extra dimensions or undiscovered particles as potential culprits. With so many competing ideas, why can't we just pick one? The challenge lies in the data, or rather, the lack of it. Dark energy leaves no direct traces. Its effects are only visible across vast distances and billions of years, making it fiendishly difficult to study. Even cutting-edge tools like the James Webb Space Telescope or future observatories like the Euclid mission can only offer indirect clues. So the mystery deepens. Is dark energy a constant force, a shifting field, or something entirely beyond our current physics? Every observation narrows the possibilities, but the truth remains just out of reach. And that's what makes this era so thrilling. We're not just mapping the cosmos, we're rewriting the rules as we go. We've been racing against an invisible clock since the moment dark energy was discovered, because its behavior doesn't just shape the universe now, it determines how everything ends. Picture a cosmic hourglass, but instead of sand, it's filled with galaxies, stars, and the very fabric of space itself. The question isn't whether time will run out, but how. Will the universe tear itself apart, freeze into eternal stillness, or collapse back into the singularity it came from? The answer hinges entirely on dark energy's secrets, and right now, scientists are staring down three terrifying possibilities. The first is the Big Rip, a scenario so violent it sounds like science fiction. If dark energy strengthens over time, becoming what theorists call phantom energy, its repulsive force could eventually overpower gravity, electromagnetism, even the bonds holding atomic nuclei together. Imagine space stretching faster and faster until first galaxies, then solar systems, then planets are ripped from each other. In the final moments, stars would explode as the space between their atoms expands too rapidly for gravity to hold them together. Even time itself could fracture. Current estimates suggest this could happen in as little as 22 billion years, a blink in cosmic terms. But what if dark energy stays constant, as the cosmological constant theory suggests? That leads us to the heat death, also known as the Big Freeze. Here, the universe keeps expanding, but at a steady pace. Galaxies drift so far apart that their light can no longer reach us, leaving every civilization in isolated darkness. Stars burn out, black holes evaporate, and space approaches absolute zero. The cosmos wouldn't end with a bang, but with an endless, silent chill, a state so bleak physicists call it maximum entropy, where not even energy can flow. Then there's the most dramatic twist of all, the Big Crunch. If dark energy weakens or reverses, gravity could regain dominance, pulling everything back together in a cosmic reversal of the Big Bang. Galaxies would collide, temperatures soar, and space itself contracts until all matter is compressed into a single point. Some theories suggest this could trigger a new Big Bang, restarting the cycle of creation. It's a tantalizing idea, but one that clashes with current observations of acceleration. So which fate awaits us? The truth is, we don't know yet. Each scenario depends on dark energy's true nature, whether it's constant, evolving, or something beyond our current models. Future telescopes might detect subtle changes in the expansion rate, offering clues. But for now, we're left with a profound realization. The universe's destiny is written in a language we're still learning to read. And every new discovery brings us closer to deciphering whether the cosmos is headed for a violent end, a silent fade, or a rebirth we can't yet imagine. Imagine two cosmic shadows lurking in the universe, one pulling everything together, the other pushing it apart. Dark matter and dark energy may sound similar, but they're like opposite players in the grand cosmic game, each shaping the universe in wildly different ways. Let's break down the biggest misconceptions. Dark matter is the invisible scaffolding of the cosmos. Think of it as the glue holding galaxies together, its gravitational pull keeping stars from flying apart as they spin. Without it, spiral galaxies like the Milky Way would tear themselves to shreds from their own rotation. We can't see dark matter directly, but its presence is betrayed by the way it bends light around galaxies, a phenomenon called gravitational lensing, and the way it tugs on visible matter like an unseen hand. Dark energy, on the other hand, isn't pulling anything. It's the phantom force stretching space itself, a cosmic repellent driving galaxies apart faster and faster. While dark matter's influence is local, shaping individual galaxies and clusters, dark energy operates on the grandest scale, dominating the entire universe's expansion. Here's where things get confusing. Both are invisible, both outweigh ordinary matter by a huge margin, and both were discovered because of their gravitational effects. But that's where the similarities end. One of the biggest myths, that dark energy and dark matter are two sides of the same coin. In reality, they're more like strangers passing in the night. Dark matter behaves like a slow, steady anchor, while dark energy is the unpredictable tide reshaping the shore. Another misconception is that they interact with each other. As far as we know, they don't. Dark energy pushes uniformly, ignoring galaxies and dark matter alike, while dark matter clumps together under gravity, completely indifferent to the expansion around it. Why does this duality matter? Because the universe we see is a battlefield between these two forces. For billions of years, dark matter's gravity dominated, slowing the expansion after the Big Bang. But around 5 billion years ago, dark energy took over, and now it's calling the shots. The fate of the cosmos hinges on this tug of war, one that we're only beginning to understand. So next time you hear about these cosmic mysteries, remember, dark matter builds the structures while dark energy dictates their destiny. and unraveling their secrets isn't just about filling textbooks, it's about rewriting the story of everything. One of the most baffling gaps in modern physics lies in the staggering mismatch between what math predicts and what the universe shows us, a problem so profound it's been called the worst theoretical prediction in the history of science. At its heart is the cosmological constant, Einstein's once discarded idea that empty space itself might harbor energy. Quantum physics tells us the vacuum of space should be seething with particles popping in and out of existence, each contributing energy. Add them all up, and theory suggests the cosmological constant should be colossal, enough to rip atoms apart before stars could even form. Yet when we measure the actual expansion of the universe, dark energy's effect is nearly 120 orders of magnitude weaker. That's like calculating the weight of an ocean but finding only a single drop of water in reality. This discrepancy isn't just a minor glitch, it reveals a chasm in our understanding of gravity, quantum mechanics, and the fabric of reality itself. Some physicists argue the numbers might cancel out through some undiscovered symmetry, like negative and positive energies balancing perfectly. Others propose that multiple universes exist, each with different constants, and we just happen to live in one where the value is bizarrely small, an idea called the anthropic principle. But these explanations feel like placeholders for a deeper truth we haven't uncovered yet. Even stranger, the observed value of the cosmological constant is oddly precise. If it were slightly stronger, galaxies would never have formed, slightly weaker, and the universe would have collapsed long ago. This fine-tuning suggests an eerie coincidence, or perhaps a clue that dark energy isn't static but dynamic, changing over time to allow life to emerge. The quest to solve this puzzle has birthed radical ideas, from extra dimensions warping the true nature of gravity to undiscovered fields that mask vacuum energy's true strength. Yet every attempt to measure or explain dark energy more precisely, like the Dark Energy Survey or upcoming experiments with the Vera Rubin Observatory, brings new layers of mystery. The cosmological constant problem isn't just a gap in our knowledge, it's a flashing sign that somewhere we've taken a wrong turn in fundamental physics. And until we find the missing piece, this remains one of science's greatest unsolved riddles, a number that holds the key to the universe's fate, written in a language we're still struggling to decode. There's something almost unsettling about the timing of dark energy's rise to power in the cosmos. Think about it. For most of the universe's history, gravity ruled unchallenged, pulling matter together to form galaxies, stars, and planets. Then, right around the time life became possible, dark energy took over like a cosmic switch flipped at the perfect moment. This isn't just a curious coincidence, it's a puzzle so perplexing scientists call it the cosmic coincidence problem. Why did dark energy become dominant precisely when it did? And what does that mean for our place in the universe? One explanation leans on the anthropic principle, the idea that the universe's laws must allow for observers like us to exist. In other words, if dark energy had been stronger earlier, galaxies would have been ripped apart before life could form. If it had been weaker, the universe might have collapsed long ago. We're here because the numbers lined up just right, a delicate balance that feels less like luck and more like a prerequisite for existence itself. Some theorists take this further, suggesting our universe might be one of many in a vast multiverse, each with different physical constants. In most of them, dark energy's strength would make life impossible, but in a rare few, conditions align perfectly and conscious beings emerge to ponder why. Not everyone finds this satisfying, though. Critics argue it's a cop-out, an answer that explains everything and nothing at once, so alternatives have emerged. One intriguing idea is that dark energy isn't constant but interacts subtly with matter, its influence waxing and waning over cosmic time. Imagine a seesaw. As galaxies formed and matter clumped together, perhaps the energy of empty space responded, ramping up its push to maintain equilibrium. Another possibility ties dark energy to the formation of large-scale cosmic structures. As the universe's web of galaxies reached a certain size, their collective gravity might have triggered dark energy's dominance, like a pressure valve releasing at just the right moment. Then there's the radical notion that we're misreading the evidence entirely. What if dark energy's apparent switch on 5 billion years ago isn't real, but a mirage caused by our incomplete understanding of gravity? Modified gravity theories propose that Einstein's equations break down on cosmic scales, making it seem like an invisible force is at work when in reality we're missing a deeper layer of physics. But these theories struggle to explain all the observations, leaving the coincidence problem wide open. So where does that leave us, staring at a cosmic riddle with no definitive answer? Whether it's the anthropic principle, an undiscovered interaction, or a flaw in our theories, this timing isn't just a curiosity, it's a clue. And cracking it could reveal whether our universe's story is one of incredible chance, hidden design, or laws we haven't even imagined yet. What if our universe isn't the only one? What if dark energy's bizarrely precise value isn't a cosmic accident, but a consequence of something far grander, a multiverse where countless universes exist, each with its own unique laws of physics? This isn't science fiction, it's one of the most compelling frameworks scientists have to explain why dark energy's strength seems so finely tuned for life. The multiverse idea emerges from string theory, a candidate for the theory of everything that suggests reality is built from tiny, vibrating strings. But here's the catch: string theory doesn't predict just one universe. Instead, it describes a vast landscape of possible universes, perhaps 10 to the 500 of them, each with different constants, dimensions, and even fundamental forces. In most of these universes, dark energy's value would be too large, ripping spacetime apart before stars could form, or too small, causing everything to collapse. But in a rare few, like ours, the numbers align perfectly. This is where the anthropic principle comes in. We find ourselves in a universe capable of hosting life because, well, we couldn't exist in the others. It's like winning a cosmic lottery where the prize is existence itself. The multiverse idea turns dark energy's fine-tuning from a baffling coincidence into an inevitable outcome of probability, a single page in an endless library of realities. But how do we test something as abstract as the multiverse? Some researchers look for imprints of other universes in the cosmic microwave background, the afterglow of the Big Bang. Others hunt for anomalies in the distribution of galaxies that might hint at collisions with parallel universes in the distant past. So far, no smoking gun has been found, but the search is far from over. Critics argue the multiverse is untestable, more philosophy than science. Yet supporters counter that it's the only framework that explains dark energy's value without invoking sheer luck. Meanwhile, string theory's landscape remains controversial, with some physicists calling it a mathematical mirage. But whether the multiverse is real or not, the very fact that dark energy drives us to consider such radical ideas shows how deeply it challenges our understanding of reality. So here we stand at the edge of a profound question. Is our universe one of many, shaped by cosmic chance, or is there a deeper principle we've yet to uncover? The answer could rewrite not just the story of dark energy, but the very meaning of existence. At the quantum level, empty space is anything but empty. It's a seething, bubbling ocean of particles popping in and out of existence in flashes of energy so brief they defy detection. These quantum fluctuations, virtual particles that appear and vanish in fractions of a second, are a cornerstone of modern physics. But here's the twist: they might also hold the key to understanding dark energy. According to quantum field theory, every cubic centimeter of space, no matter how seemingly empty, should thrum with this vacuum energy. Add it all up across the universe, and the numbers should be staggering enough to warp spacetime on a cosmic scale. This is where the puzzle begins. If vacuum energy is real, and if it fuels dark energy, why is its observed effect so vanishingly weak? The math predicts a cosmological constant so enormous it would have ripped the universe apart moments after the Big Bang. Yet when we measure dark energy's actual influence, it's almost 120 orders of magnitude smaller than theory suggests. That's like expecting a tsunami and finding only a ripple. Scientists call this the vacuum catastrophe, and it's one of the most glaring mismatches between prediction and reality in all of physics. So what's going wrong? One possibility is that we're missing a crucial piece of the puzzle. Maybe undiscovered symmetries in nature cancel out most of this energy, leaving only the faintest remnant we now call dark energy. String theory offers another angle. Extra dimensions could be diluting the true strength of vacuum energy, making it appear weaker in our four-dimensional reality. Or perhaps vacuum energy isn't uniform but varies across space in ways we haven't yet detected, averaging out to the subtle effect we observe. But the most radical idea is that vacuum energy and dark energy aren't the same thing at all. Vacuum energy, as quantum theory describes it, might be real but irrelevant to cosmic expansion, a background hum drowned out by something far stranger. This would mean dark energy arises from an entirely different source, like an undiscovered field or a flaw in Einstein's gravity. The stakes couldn't be higher. If vacuum energy is the culprit, it would bridge quantum mechanics and cosmology, two pillars of physics currently at odds. If it's not, we might need to rewrite the rules of the universe. Every new observation, from particle colliders to deep space telescopes, brings us closer to an answer, or deeper into the mystery. One thing's certain: the quantum vacuum isn't just empty darkness. It's a frontier, and solving its secrets could change everything we know about the cosmos. If dark energy is the unseen force accelerating the universe's expansion, then its fingerprints should be all over the largest structures in existence. The cosmic web of galaxy clusters, filaments, and vast empty voids that stretch across billions of light years. But here's the catch: dark energy doesn't just push galaxies apart, it alters the very blueprint of the cosmos, shaping how matter clumps together over time. To understand this, picture the universe as a growing loaf of raisin bread. As the dough expands, the raisin's galaxies move away from each other. But dark energy isn't just stretching the dough, it's changing how the raisins cluster, slowing the formation of new structures while magnifying the emptiness between them. This influence becomes starkly visible in galaxy surveys like the Sloan Digital Sky Survey, which has mapped millions of galaxies across cosmic history. By studying the distribution of these galaxies, scientists can spot dark energy's subtle handiwork. For instance, in a universe dominated by gravity alone, galaxy clusters would grow denser and more numerous over time as matter collapses under its own weight. But observations reveal something unexpected. Clusters aren't forming as efficiently as they should be. Dark energy's repulsive push acts like a cosmic brake, stifling the growth of these titanic structures. The effect is subtle, just a few % difference in cluster counts, but it's there, etched into the data like a shadow. Even more telling are the voids, the vast, empty regions spanning hundreds of millions of light years. These cosmic deserts are expanding faster than the universe itself, their boundaries stretching as dark energy flings galaxies away from their edges. Surveys show voids growing larger and more isolated over time, as if space itself is being hollowed out from within. The Sloan data reveals this in startling detail. Voids in the early universe were smaller and more interconnected, but today they're like bubbles in an inflating foam, pushed apart by an invisible force. What makes this mystery so profound is the timescale. Dark energy's dominance began around 5 billion years ago, a mere blink in cosmic terms, yet its impact is already visible in the way structures evolve. Future telescopes like the Vera Rubin Observatory we'll delve even deeper, mapping billions of galaxies to trace how dark energy reshapes the universe's skeleton. Each new dataset brings us closer to answering a haunting question. Is this acceleration a constant force, or is it changing, quietly rewriting the fate of everything we see? Even as dark energy reshapes our understanding of cosmic expansion, another mystery lurks in the data, one so stubborn it's been dubbed the Hubble tension. At its core, this puzzle revolves around a simple question: how fast is the universe expanding right now? You'd think we'd have a clear answer, but here's the catch. Two of our most trusted methods for measuring this rate, the Hubble constant, are giving us wildly different results. One approach studies the cosmic microwave background, the faint afterglow of the Big Bang, and suggests the universe is expanding at around 67 kilometers per second per megaparsec. The other relies on nearby supernovae and pulsating stars, pointing to a faster rate of 73. That gap might seem small, but in cosmology, it's a glaring discrepancy. And dark energy might be the missing piece that explains why. Let's break it down. The first method, using the Planck satellite's observations of the early universe, assumes a predictable timeline of cosmic evolution based on our best models. It's like reconstructing a car's speed by examining its tire track. If you know the road's conditions, you can work backward to find how fast it was moving. But the second method, which measures distances to nearby stars and galaxies, is more like clocking the car's speed directly with a radar gun. The fact that these two numbers don't match suggests something's off. Either our measurements are flawed, or our understanding of the universe's road conditions is incomplete. This is where dark energy enters the picture. If its strength isn't constant, as many assume, but has changed over time, it could skew the expansion rate in ways we haven't accounted for. Imagine a car that didn't just accelerate steadily but lurched forward unpredictably. Our models, built on smooth acceleration, would misfire. Some theorists propose that dark energy might have kicked in earlier than we thought, tweaking the universe's expansion history just enough to explain the tension. Others speculate that dark energy interacts with dark matter in ways that subtly alter galactic motions, throwing off local measurements. Then there's the radical possibility that we're missing something fundamental, an undiscovered particle, a flaw in Einstein's gravity, or even evidence of parallel universes nudging our own. Each hypothesis comes with its own challenges, but all share one unsettling implication. Our cosmic rulebook might need rewriting. Future telescopes, like the Nancy Grace Roman Space Telescope, aim to settle the debate by mapping millions of galaxies with unprecedented precision. Until then, the Hubble tension isn't just a technical glitch, it's a beacon, drawing us toward a deeper truth about dark energy, the universe's expansion, and perhaps the very laws that govern reality itself. What if dark energy isn't real at all? What if the cosmic acceleration we observe isn't driven by an invisible force, but by a fundamental flaw in our understanding of gravity itself? This radical idea lies at the heart of modified gravity theories, frameworks that rewrite Einstein's equations to explain the universe's expansion without invoking dark energy. The most famous of these is modified Newtonian dynamics, or MUND, proposed in the early 1980s to explain quirks in galactic rotation. MUND suggests that gravity behaves differently at extremely low accelerations, the kind found in the outskirts of galaxies. Instead of requiring dark matter to explain why stars orbit faster than expected, MUND tweaks the math so gravity weakens less rapidly over large distances. At first glance, it's an elegant fix, but when applied to the entire universe, MUND struggles to match the observed acceleration without additional tweaks. Enter F of our gravity, a more sophisticated contender. Unlike MUND, which alters Newton's laws, F of our gravity revises Einstein's general relativity by introducing extra terms into the equations. Picture gravity not as a simple curvature of space-time, but as a complex landscape with hidden folds and contours. In this model, the universe's accelerated expansion emerges naturally from these modified dynamics, no dark energy needed. Early versions of F of R gravity showed promise, reproducing cosmic acceleration while matching observations of galaxy clusters. But there's a catch. Many of these models predict subtle deviations in the way light bends around massive objects, discrepancies that haven't been confirmed by telescopes. The debate doesn't end there. Some theories propose gravity leaks into extra dimensions, weakening its grip on cosmic scales and mimicking dark energy's effects. Others suggest gravity grows stronger over vast distances, counterintuitively driving expansion. Each idea offers a tantalizing escape from the dark energy puzzle, but they all face the same hurdle: precision data. Measurements of the cosmic microwave background, galaxy clustering, and distant supernova consistently favor the standard dark energy model, lambda CDM. Modified gravity theories often require convoluted adjustments to fit these observations, stripping them of their initial simplicity, yet the allure remains. If one of these alternatives is correct, it would revolutionize physics, unifying cosmic acceleration with the rest of gravity's behavior. The challenge: finding a smoking gun, a clear observational signature that distinguishes modified gravity from dark energy. Future missions like the European Space Agency's Euclid telescope might settle the debate by mapping the universe's expansion with unprecedented detail. Until then, these theories stand as bold reminders that our understanding of gravity and the cosmos might still be missing a crucial chapter. Among all the possible fates of the universe, none is more violent or more bizarre than the Big Rip. This apocalyptic scenario hinges on a specific flavor of dark energy known as phantom energy, a hypothetical form so potent it doesn't just accelerate the universe's expansion, it escalates. Unlike ordinary dark energy, which pushes galaxies apart at a steady rate, phantom energy grows stronger as space expands, creating a terrifying feedback loop. Picture a rubber band being stretched, but instead of resisting, it becomes easier to pull the more it elongates. Now imagine that rubber band is space-time itself, and you begin to grasp the sheer destructive power of this theoretical force. The mechanics of a Big Rip are as chilling as they are straightforward. As phantom energy intensifies, its repulsive force eventually overpowers gravity's grip on galaxy clusters, then individual galaxies, then solar systems. Stars would be ripped from their orbits, planets torn from their suns, but the horror doesn't stop there. In the final moments, even atomic bonds would fail, with protons and electrons wrenched apart as the space between them expands faster than the speed of light. The universe wouldn't just end, it would disintegrate from the inside out, leaving behind a desolate, empty void where structure itself is impossible. Could this really happen? Current observations leave the door open. The equation governing phantom energy hinges on a single parameter, W, which describes how dark energy's pressure relates to its density. If W is exactly -1, dark energy behaves like Einstein's cosmological constant, unchanging and steady. But if W dips even slightly below -1, the universe could be headed for a rip. So far, measurements hover tantalizingly close to the threshold, with margins of error just wide enough to keep theorists on edge. The Dark Energy Survey's latest data places W at around -1.01, plus or minus a few hundredths, a number that could imply a big rip in roughly 22 billion years. Yet there's a catch. Phantom energy violates certain energy conditions in physics, hinting that it might be inherently unstable or impossible. Some models suggest it could trigger quantum vacuum decay, where space-time itself cracks into a lower energy state, rewriting the laws of physics in an instant. Others argue phantom energy is merely a mathematical quirk, a mirage caused by our incomplete understanding of cosmic acceleration. The truth is, we're still gathering clues. Upcoming missions like the Euclid Space Telescope will refine measurements of W, potentially ruling phantom energy in or out. But until then, the Big Rip remains a haunting reminder of how fragile our cosmic home might be, and how much we still don't understand about the dark force shaping its destiny. The story of dark energy isn't just about the universe's present acceleration. It might stretch all the way back to the very first moments of creation. Rewind the cosmic clock to a fraction of a second after the Big Bang, and you'll find a period of exponential expansion called inflation, where the universe doubled in size countless times faster than the blink of an eye. This explosive growth smoothed out the cosmos, leaving behind the seeds of galaxies we see today. But here's the tantalizing question. Could the same mysterious force driving cosmic acceleration now, dark energy, have played a role back then? At first glance, inflation and dark energy seem like cosmic opposites. Inflation was unimaginably short and violent, while dark energy's influence is slow, steady, and subtle. Yet both involve a form of energy embedded in space itself, stretching the fabric of reality. Some theorists speculate they might be two faces of the same phenomenon, different intensities of a single underlying mechanism. If true, dark energy wouldn't just shape the universe's fate, it would have helped birth its structure. One clue lies in primordial gravitational waves, ripples in space-time generated during inflation. These faint echoes, if detected with precision, could reveal whether inflation's energy behaved like a cosmological constant, just as dark energy does today. Experiments like the upcoming Light-Bird satellite aim to hunt for these waves in the cosmic microwave background, the afterglow of the Big Bang. A match in the signatures of early and late-time expansion would be groundbreaking, hinting at a cosmic thread tying the universe's birth to its death. But the plot thickens. Some models suggest dark energy wasn't always dormant. Could it have flickered to life in brief bursts during the early universe, leaving imprints in the distribution of galaxies or the formation of black holes? Others propose that dark energy is a relic of inflation's end, a leftover energy that faded into obscurity before reawakening billions of years later. The challenge is that the early universe's extreme density would have masked dark energy's subtle push, making its fingerprints incredibly hard to trace. What's certain is this: if dark energy was active during cosmic dawn, it would rewrite our understanding of its nature. Instead of a latecomer to the universe's story, it could be a constant, shape-shifting presence, one that's been weaving the cosmos's fate since the very beginning. If dark energy holds the key to the universe's accelerating expansion, then the equation of state parameter represented by the letter W is the dial controlling its intensity. This single number determines whether dark energy is a constant force, a dynamic field, or something far more exotic. Think of it like a cosmic thermostat. Set W to exactly -1, and dark energy behaves like Einstein's cosmological constant, a steady pressure woven into space-time itself. But tweak that value even slightly, and the universe's fate veers into dramatically different territory. A value slightly above -1 could mean dark energy weakens over time, potentially allowing gravity to regain control. Dip below -1 and you're in phantom energy territory, where the universe's expansion spirals toward a catastrophic Big Rip. Pinpointing W isn't just academic, it's a race against time to forecast the cosmos's ultimate destiny. Current experiments like the Dark Energy Survey and the Planck satellite have narrowed W to around -1.01, with error bars hovering just above and below that critical threshold. These measurements come from observing distant supernova, galaxy clustering, and the cosmic microwave background, each offering a piece of the puzzle. But here's the catch: the data isn't unanimous. Some observations hint at a W that's not perfectly constant, suggesting dark energy's strength might fluctuate across cosmic epochs. The stakes couldn't be higher. If W varies, it implies dark energy isn't a static backdrop but an active player that evolves with the universe. Imagine discovering that the force shaping reality today behaved differently 5 billion years ago, or might change again in the future. Upcoming missions like the Euclid Space Telescope aim to measure W with unprecedented precision, scouring billions of galaxies for subtle clues. Until then, this parameter remains one of cosmology's most tantalizing unknowns, a single number holding the answer to whether our universe will fade, freeze, or fracture. What if dark energy isn't the unchanging force we've assumed it to be? The idea that its strength could shift over cosmic time isn't just a minor tweak to our models, it's a revolution waiting to happen. Right now, most theories treat dark energy as a constant, like an immutable law written into the fabric of space. But what if it's more like a dial being slowly turned, growing stronger or weaker as the universe ages? This possibility isn't just speculative, it's rooted in real anomalies buried in the data. Some observations of distant supernovae suggest dark energy's push might have been slightly weaker in the past, while measurements of galaxy clusters hint it could be strengthening today. The implications are staggering. A dynamic dark energy wouldn't just alter the universe's fate, it would rewrite the rules we use to predict it. The hunt for these variations hinges on a delicate cosmic detective game. Imagine trying to measure a force that leaves no direct trace, using only its faint imprint on the light of galaxies billions of years old. One key tool is baryon acoustic oscillations, ripples frozen into the distribution of matter during the universe's infancy. By mapping how these ripples stretch over time, scientists can track changes in dark energy's influence. Projects like the Dark Energy Spectroscopic Instrument are scanning millions of galaxies to create a 3D cosmic timeline, searching for subtle bends in the curve that might betray dark energy's shifting nature. Another approach studies the growth of galaxy clusters, whose formation rates should slow under dark energy's push. If those rates don't match predictions across different epochs, it could signal that the force driving expansion isn't constant after all. But the real game changer lies just over the horizon. The Euclid Space Telescope, launched in 2023, is designed to measure the universe's expansion with razor-sharp precision across 10 billion years of cosmic history. Its infrared eyes will peer deeper into the past than any instrument before, hunting for deviations in the way dark energy sculpts spacetime. Meanwhile, the Vera Rubin Observatory's decade-long legacy survey of space and time will capture time-lapses of billions of galaxies, watching for unexpected accelerations or slowdowns in their drift. These missions could uncover pattern cycles of ebb and flow in dark energy's strength that current models can't explain. Here's where things get even stranger. If dark energy does vary, it might not be alone. Some theories propose it's intertwined with dark matter, their interplay shaping the cosmos in ways we've yet to fathom. Others suggest it's linked to an undiscovered quantum field, its fluctuations echoing changes in dark energy's push. The most radical ideas posit that dark energy isn't a force at all, but a symptom of spacetime itself evolving, its properties shifting as the universe ages. Each possibility opens doors to uncharted territories of physics where the constants we take for granted might not be so constant after all. The stakes couldn't be higher. A universe with static dark energy faces a slow, cold demise. But if this force is changing, all bets are off. It could mean the cosmos is headed for a collapse we can't yet see, or an expansion so violent it defies imagination. Every new observation brings us closer to the truth, but for now, one thing is certain. The story of dark energy is still being written, and its next chapter might surprise us all. Black holes, those cosmic vacuum cleaners lurking in the depths of space, might seem like the last place to look for clues about dark energy. But what if these monstrous gravitational traps hold a key to understanding the universe's accelerating expansion? One of the most startling theories suggests that dark energy isn't just influenced by black holes, it might be created by them. At first glance, the idea seems absurd. After all, black holes are known for pulling everything in, while dark energy pushes everything apart. Yet when we peer into the math, a strange connection emerges. Take the concept of black hole entropy, a measure of the disorder or information contained within a black hole's event horizon. In the 1970s, physicist Stephen Hawking showed that black holes aren't just simple, empty pits. They have temperature, they radiate energy, and they possess entropy proportional to their surface area. Fast forward to today, and some theorists argue that this entropy could be linked to dark energy on a cosmic scale. Imagine the universe as a hologram, with all the information about its contents, stars, galaxies, even dark energy, encoded on its boundary. In this wild framework, black holes act like cosmic pixels, their combined entropy somehow generating the repulsive force we call dark energy. Even more speculative is the idea of holographic dark energy, inspired by string theory's suggestion that our three-dimensional universe might be a projection of information stored on a two-dimensional surface. In this model, dark energy's density is tied to the size of the universe's horizon, the maximum distance light could have traveled since the Big Bang. Black holes, as regions where space and time are profoundly warped, could be twisting this horizon in ways that amplify dark energy's effects. Some calculations even suggest that the total dark energy in the universe matches the energy you'd expect if all the information trapped in black holes were converted into this mysterious force. But how do we test these mind-bending ideas? One clue might lie in the growth of supermassive black holes at the hearts of galaxies. If dark energy is truly entangled with black hole entropy, then the way these monsters evolve over cosmic time should leave fingerprints in the universe's expansion rate. Observations from telescopes like LIGO, which detect ripples from colliding black holes, could also reveal unexpected links between gravity and dark energy. Of course, not everyone's convinced. Critics point out that black holes are local phenomena, while dark energy operates on the grandest scales. Why would something as specific as a black hole's entropy govern the entire universe's expansion? Others argue these theories are elegant but untestable beautiful math without observable consequences. Yet as we push deeper into the cosmos, the line between black holes and dark energy grows blurrier, hinting at a connection we're only beginning to grasp. Whether it's entropy, holograms, or something even stranger, one thing's clear. In the hunt for dark energy's origins, black holes might be hiding more secrets than we ever imagined. To uncover dark energy's fingerprints, we don't just look at distant galaxies, we peer back to the universe's baby picture, the cosmic microwave background. This faint glow, emitted just 380,000 years after the Big Bang, is more than a relic of the past. It's a cosmic chalkboard where dark energy scrawled its signature in subtle distortions. When satellites like WMAP and Planck mapped this radiation with exquisite precision, they revealed patterns that shouldn't exist unless something was stretching the fabric of spacetime itself. The telltale clues lie in the way the CMB's temperature fluctuations are spaced across the sky. Imagine dropping pebbles into a pond, the ripples spread in predictable rings. But if someone started stretching the pond's surface as the ripples moved, those rings would distort, their spacing warped by the unseen force. That's essentially what dark energy does to the CMB. As the universe expanded, dark energy's push altered how these primordial ripples froze into place, leaving them slightly more spread out than gravity alone could explain. Planck's measurements detected this anomaly with staggering accuracy, pinpointing dark energy's contribution to the universe's energy budget at around 68%, a figure that aligns eerily with supernova observations. But the CMB doesn't just confirm dark energy's existence, it unveils its timing. By studying the polarization of this ancient light, subtle swirls caused by gravitational waves from the early universe scientists traced when dark energy turned on. The data suggests it was always present, lurking in the background like a dormant force, until 5 billion years ago when it overpowered gravity and began accelerating the cosmos. This cosmic coup didn't just reshape the future, it left echoes in the CMB's large-scale structure, where the positions of hot and cold spots betrayed dark energy's silent takeover. Yet mysteries linger. Some regions of the CMB appear cooler than expected, as if dark energy's influence isn't perfectly uniform. Could this hint at variations in its strength, or even a connection to the elusive dark flow, a controversial phenomenon where galaxy clusters seem to stream toward an unseen attractor? Others point to the CMB's lensing patterns, where dark energy bends the light of the early universe like a funhouse mirror, creating faint smudges that Planck's team used to map its distribution. These imprints are so delicate that detecting them required measuring temperature differences of a millionth of a degree, a feat akin to spotting a snowflake's shadow from orbit. What makes these findings so revolutionary is their independence. Unlike supernova measurements, which rely on the brightness of exploding stars, or galaxy surveys that track cosmic structures, the CMB offers a pristine snapshot of dark energy's role before galaxies even existed. It's a time capsule untainted by the messy evolution of matter, and its message is clear. Dark energy isn't just a latecomer to the cosmic story, it's been shaping the plot since the very first pages. As future missions like the Simons Observatory refine these measurements, they'll hunt for even fainter whispers in the CMB signs of dark energy's potential interactions with dark matter or shifts in its strength over time. For now, this ancient light remains one of our most powerful tools, illuminating the invisible force that's rewriting the universe's destiny. The next decade could rewrite everything we know about dark energy, thanks to a new generation of telescopes and missions designed to hunt this invisible force with unprecedented precision. Leading the charge is the Euclid Space Telescope, a European Space Agency mission launched in 2023 with one singular goal: to create the most detailed 3D map of the universe ever assembled. By measuring the shapes and positions of billions of galaxies across 10 billion light-years, Euclid will trace how dark energy has stretched the cosmic web over time. But here's the revolutionary part: it won't just look at galaxies. Euclid's infrared eyes will peer through cosmic dust, capturing faint distortions in spacetime caused by dark energy's push, a phenomenon called weak gravitational lensing. These distortions are like fingerprints, revealing not just where dark energy is, but how its strength may have changed across cosmic epochs. Meanwhile, on Earth, the Vera Rubin Observatory's legacy survey of space and time is set to begin its ambitious 10-year scan of the southern sky. With a camera the size of a small car, Rubin will detect subtle shifts in the brightness and motion of billions of galaxies, effectively making a time-lapse of the universe's expansion. One of its key targets, baryon acoustic oscillations, frozen ripples from the early universe that act as cosmic yardsticks. If dark energy's push varies over time, these ripples should stretch in telltale ways, offering clues no other instrument can match. Then there's the James Webb Space Telescope, already reshaping our understanding of the cosmos. While JWST wasn't designed specifically for dark energy, its ability to see the universe's first galaxies provides a critical baseline. By comparing ancient star systems to modern ones, scientists can track how dark energy's influence has evolved since the dawn of time. JWST infrared vision also pierces through obscuring dust, revealing supernovae in pristine detail. The same kind of stellar explosions that first betrayed dark energy's existence decades ago. But perhaps the most daring experiment is the proposed LISA mission, a space-based gravitational wave detector. If dark energy interacts with gravity in unexpected ways, mergers of supermassive black holes could carry faint echoes of that interaction in their spacetime ripples. LISA's ability to sense these low-frequency waves might uncover a hidden dialogue between dark energy and gravity, rewriting the rules we thought governed the cosmos. The stakes couldn't be higher. Each of these missions tackles dark energy from a different angle, like detectives piecing together a puzzle from scattered clues. If they converge on the same answer, whether it's a varying dark energy, a flaw in gravity, or something entirely new, we could witness a revolution in physics as profound as Einstein's revelation of relativity. And if their findings clash, that might be even more exciting, signaling a cosmic mystery deeper than we ever imagined. One thing's certain, the era of guessing is ending. The age of answers is about to begin. Einstein's theory of general relativity paints gravity as the curvature of space-time, a smooth, continuous landscape shaped by massive objects. Quantum mechanics, on the other hand, describes a frenetic, granular world where particles flicker in and out of existence and forces act in discrete packets. These two pillars of physics work flawlessly in their own domains, but when it comes to dark energy, they clash spectacularly. Unifying them into a single framework, quantum gravity might finally explain why dark energy exists at all and why its effects are so bafflingly faint. One of the most promising candidates for quantum gravity is string theory, which suggests that all particles are minuscule vibrating strings. In this framework, dark energy could emerge from the way these strings interact with extra dimensions, hypothetical layers of reality coiled into spaces too tiny to detect. Imagine spacetime as a vast ocean and dark energy as the subtle pressure of hidden currents flowing through dimensions we can't see. Some string models even predict a landscape of possible universes, each with different amounts of dark energy, placing ours in a rare sweet spot where life can exist. But there's a catch. String theory is notoriously difficult to test, and no experiment has yet confirmed its predictions. Another approach, loop quantum gravity, treats spacetime itself as woven from tiny, discrete loops. Here, dark energy might arise from the way these loops twist and knot at the universe's largest scales, creating an emergent force that looks like cosmic acceleration. Think of it like a cosmic tapestry. The tighter the weave, the more resistance there is to stretching, which could mimic dark energy's repulsive push. Yet this theory, too, struggles to explain why the observed value of dark energy is so vanishingly small compared to quantum predictions. The real headache comes when we try to reconcile quantum field theory with gravity. According to quantum rules, empty space should be teeming with virtual particles, each contributing energy to the vacuum. Summing up all these contributions should make the cosmological constant, dark energy's theoretical counterpart, enormous. Yet in reality, it's almost zero. This discrepancy, known as the vacuum catastrophe, suggests we're missing something fundamental. Some physicists argue that unknown symmetries cancel out most of this energy, leaving behind the faint residue we call dark energy. Others propose that gravity itself behaves differently at quantum scales, perhaps leaking into extra dimensions and diluting its effect. The stakes couldn't be higher. If quantum gravity can explain dark energy, it wouldn't just solve a cosmic mystery, it would revolutionize our understanding of reality. Until then, the hunt continues with experiments like the Laser Interferometer Gravitational Wave Observatory probing the quantum nature of spacetime, and theorists scrambling to bridge the gap between the infinitely large and the infinitesimally small. One thing's certain, in the quest to unify these theories, dark energy isn't just a puzzle, it's the ultimate litmus test. What if our three-dimensional universe is nothing more than a projection, a cosmic hologram where everything we see, from the tiniest atom to the vastest galaxy, is encoded on a two-dimensional surface at the edge of reality? This is the essence of the holographic principle, a radical idea born from the clash between quantum mechanics and black hole physics, and it might hold the key to unraveling dark energy's deepest secrets. The story begins with black holes. In the 1970s, physicist Jacob Bekenstein discovered something astonishing. A black hole's entropy, a measure of its hidden information, isn't proportional to its volume as you'd expect, but to its surface area. This hinted that all the information swallowed by a black hole might be stored on its event horizon, the boundary where light can no longer escape. Fast forward a few decades, and theorists like Leonard Susskind proposed this wasn't just true for black holes, it might apply to the entire universe. Imagine reality as a gigantic cosmic hard drive, with every event, every particle, every law of physics encoded on a distant two-dimensional shell, our three-dimensional experience. Just an incredibly detailed illusion. So where does dark energy fit in? Some models suggest it's not a force at all, but a side effect of this holographic encoding. Picture the universe's boundary as a vibrating membrane humming with quantum information. As the cosmos expands, that boundary grows, and the way information is projected inward could create the illusion of an outward push, what we perceive as dark energy. In this view, cosmic acceleration isn't driven by an invisible energy field, but by the way space-time renders reality from its underlying code. The math gets even wilder. One specific holographic model, called the holographic dark energy theory, proposes that the amount of dark energy in the universe is directly tied to the size of the cosmic horizon, the maximum distance light could have traveled since the Big Bang. As the horizon expands, so does the screen where information is stored, subtly altering how energy manifests in our three-dimensional projection. The numbers align eerily well with observations, suggesting dark energy's strength isn't arbitrary but dictated by the universe's informational architecture. But how could we test something so abstract? One clue might lie in the cosmic microwave background. If dark energy is truly holographic, its influence on the early universe's expansion should leave faint statistical fingerprints, subtle deviations in the way temperature fluctuations are distributed across the sky. Future telescopes like the Simons Observatory could hunt for these anomalies. Another approach studies black hole mergers. If space-time is fundamentally holographic, gravitational waves from these collisions might carry telltale signatures of hidden dimensions or information-theoretic effects. Not everyone's convinced, of course. Critics argue the holographic principle, while elegant, is still more metaphor than rigorous physics. Without a way to directly observe the universe's boundary, it's hard to prove whether dark energy's holographic explanation is profound truth or mathematical poetry. Yet the very fact that such an outlandish idea fits the data so well speaks to how deeply dark energy challenges our understanding. Whether it's holograms, quantum fields, or something even stranger, one thing is clear. The universe's greatest mystery might not be a force at all, but a message written in the language of information itself. The eerie precision of dark energy's strength doesn't just defy physics, it rattles our understanding of existence itself. Why does this mysterious force have exactly the right value to allow galaxies, stars, and ultimately life to form? The numbers are so delicate that if dark energy were even slightly stronger, the universe would have expanded too rapidly for matter to clump together. Slightly weaker, and gravity would have crushed everything back into a cosmic singularity long before life could emerge. This bizarre fine-tuning has led some scientists to ask a question that blurs the line between physics and philosophy. Is dark energy's value evidence of a universe tailored for life? At the heart of this debate lies the anthropic principle, the idea that the universe's fundamental constants must be compatible with the existence of observers like us. In its weakest form, it's almost a tautology. We can only measure the universe from within a universe that allows our existence. But taken further, it suggests a staggering possibility, that dark energy's value isn't random but constrained by the necessity for life to arise. Nobel laureate Steven Weinberg once calculated that if dark energy were just 10 times stronger, galaxies would never have formed. The fact that it's so perfectly balanced seems less like luck and more like a prerequisite for conscious beings to ponder it at all. Critics push back hard. To them, invoking the anthropic principle feels like giving up, a retreat into metaphysics when physics should demand testable explanations. They argue that calling dark energy fine-tuned is backwards. Life adapted to the universe's conditions, not the other way around. Imagine a puddle marveling that the hole it fills fits it perfectly, not realizing the water simply conformed to the cavity. Yet even skeptics admit the coincidence is jarring. The cosmological constant's observed value is a decimal point followed by 120 zeros before the first significant digit, a number so preposterously small that calling it accidental strains credulity. This tension has birthed radical alternatives. One camp proposes a multiverse, a vast ensemble of universes, each with different physical constants. In most, dark energy's strength would make life impossible. But in a vanishingly rare subset, the numbers align and observers emerge to wonder why. It's a cosmic lottery where winning tickets are universes like ours. Others suggest dark energy isn't constant but dynamic, evolving over time to allow complexity to flourish. Some theories even posit a feedback loop. The emergence of conscious observers somehow stabilizes dark energy's value, intertwining life with the cosmos's fundamental fabric. The debate spills beyond physics into theology and epistemology. Does fine-tuning imply a designer, as some religious scholars argue? Or is it a statistical inevitability in an infinite multiverse? And if we accept the anthropic principle, does it stifle scientific curiosity by treating dark energy's value as a foregone conclusion? These questions have no easy answers, but they underscore how deeply dark energy challenges not just our equations, but our very sense of place in the universe. What's undeniable is that dark energy's precision forces us to confront the limits of our theories. Whether it's a cosmic coincidence, a multiverse selection effect, or something beyond our current imagination, one thing is clear: the universe didn't have to be this way. And yet, here we are, living proof that against astronomical odds, it is. What if the key to dark energy's mysteries lies not in our familiar three dimensions, but in realms we can't even see? Some of the boldest theories in physics suggest that dark energy might be leaking into our universe from hidden dimensions, secret layers of reality, curled up so tightly they're invisible to us. This isn't science fiction. It's a serious possibility emerging from string theory, where our entire cosmos could be floating like a membrane or brain in a higher dimensional space. Imagine reality as a loaf of bread, with each slice representing a separate universe. Dark energy might be the pressure from adjacent slices pressing against ours, warping space-time in ways we perceive as cosmic acceleration. One compelling version of this idea comes from the brain world scenario, where our three-dimensional universe is embedded in a higher dimensional bulk. In this model, gravity, unlike other forces, isn't confined to our brain. It spills into the extra dimensions, weakening its grip over vast distances. This leakage could explain why dark energy's repulsive force only becomes noticeable on cosmic scales, overpowering gravity as the universe expands. Picture a sponge soaking up water. Gravity's strength dissipates into the higher dimensions, while dark energy's push remains concentrated, tilting the cosmic balance. The math gets even wilder when you consider the Kaluza-Klein theory, an early attempt to unify gravity and electromagnetism by adding a fourth spatial dimension. Modern adaptations suggest that dark energy could arise from vibrations in these hidden dimensions, tiny, coiled-up spaces a billionth the size of an atom. These vibrations might generate a field permeating our universe, its energy driving expansion like an invisible engine. Some calculations even hint that the size of these extra dimensions determines dark energy's strength, offering an explanation for its bafflingly small but non-zero value. But how do we test something so abstract? One clue might come from gravitational waves. If higher dimensions exist, ripples in space-time from colliding black holes could carry faint echoes of their presence, subtle distortions betraying where gravity escaped into other realms. Experiments like LIGO are already hunting for these anomalies. Another approach involves particle colliders. If extra dimensions exist, smashing protons together at near light speeds might briefly create particles that flicker into these hidden layers, leaving behind missing energy signatures in detectors. Critics argue these ideas stretch plausibility, with no direct evidence yet for extra dimensions. Yet the very fact that dark energy drives us to consider such radical solutions underscores how deeply it challenges our understanding. Whether it's brains, vibrating strings, or unseen dimensions, one thing is clear. The answer to dark energy might not lie in our universe at all, but in the invisible architecture surrounding it. Among the most elusive particles in the universe, neutrinos, those ghostly, nearly massless entities that stream through matter as if it weren't even there, might hold an unexpected clue to dark energy's secrets. These cosmic phantoms, born in the hearts of stars and violent stellar explosions, barely interact with anything, yet their tiny masses could be subtly shaping the universe's accelerating expansion. The connection seems improbable at first glance, but when you dig into the math, a startling possibility emerges. What if dark energy isn't just a static force, but something dynamic, entangled with the behavior of these shadowy particles? Neutrinos are already full of surprises. For decades, physicists thought they were completely massless, until experiments revealed they oscillate between different types, a phenomenon only possible if they have some infinitesimal weight. Current estimates place their combined mass at around 1/10,000th of an electron's, but here's the catch. Even that minuscule value could have cosmic consequences. In the early universe, neutrinos were ultra-relativistic, zipping around at near light speed. But as space expanded and cooled, they slowed down, transitioning into non-relativistic particles whose gravitational influence began to clump matter together. Around the same epoch, roughly 5 billion years ago, dark energy became dominant. Coincidence? Some theorists think not. One provocative idea suggests that dark energy's emergence might be tied to neutrinos crossing a critical energy threshold. Picture a seesaw. As neutrinos lost energy, their weakening gravitational pull could have allowed dark energy's repulsive force to tip the cosmic balance. Intriguingly, certain modified gravity models predict this exact timing, with neutrino masses acting as a hidden variable that triggers acceleration. If true, it would mean dark energy isn't entirely independent. It's part of a delicate interplay between the universe's smallest particles and its largest scale structure. Then there's the neutrino dark energy hypothesis, which takes the connection even further. In this scenario, neutrinos don't just influence dark energy, they are dark energy, or at least a component of it. The theory proposes that as neutrinos decelerated, their quantum fields could have generated a repulsive force mimicking dark energy's effects. It's a stretch, but not impossible. Similar mechanisms appear in theories where particles called accelerons interact with neutrinos to create a cosmic pressure. The challenge: neutrinos are notoriously hard to pin down. Billions pass through your body every second without a trace, and their minuscule masses are still only roughly estimated. That uncertainty is where things get fascinating. If neutrinos are heavier than we think, their gravitational tug might alter how galaxies cluster in ways that mimic or mask dark energy's influence. Experiments like the Karlsruhe tritium neutrino experiment are racing to nail down their exact mass, while cosmological surveys scrutinize whether neutrino-rich regions of space show anomalies in expansion rates. Even more tantalizing are hints that neutrinos might not all behave the same way. If some are sterile neutrinos, a hypothetical fourth flavor that interacts only via gravity, they could be leaking energy into hidden dimensions, indirectly fueling dark energy's push. Of course, skeptics argue these ideas are speculative at best. After all, neutrinos are billions of times lighter than protons, making their gravitational impact seem negligible. Yet history has taught us that the universe often hides its most profound truths in the subtlest details. Whether neutrinos are a missing piece of the dark energy puzzle or just another red herring, their story is a reminder that sometimes the smallest things cast the longest shadows. Imagine holding a map of the universe's oldest light, the cosmic microwave background, and discovering it's not just randomly speckled with hot and cold spots, but eerily aligned along a specific axis. This isn't science fiction, it's the axis of evil, one of cosmology's most perplexing anomalies. Named half-jokingly for its defiance of standard models, this mysterious alignment in the CMB's temperature fluctuations points in a particular direction, as if the universe itself has a hidden compass. And dark energy, already the universe's greatest enigma, might be the unseen hand behind this cosmic conspiracy. The story begins with the Wilkinson microwave anisotropy probe, which first mapped the CMB in exquisite detail. Scientists expected the temperature variations to be randomly distributed, reflecting the primordial chaos of the Big Bang. Instead, they found a peculiar pattern. The hot and cold spots weren't scattered haphazardly, but seemed to line up along a specific axis like beads on a string stretching across the sky. Later observations by the Planck satellite confirmed the anomaly, deepening the mystery. Statistically, the odds of this happening by chance are astronomically lower, around 1 in 10,000. So what's really going on? One provocative theory suggests dark energy isn't uniform but directional, its influence stronger in certain regions of space. Picture a breeze blowing across a pond, creating ripples that all tilt slightly in one direction. If dark energy's push varies across the cosmos, it could have subtly tilted the universe's expansion during inflation, leaving behind this ghostly axis in the CMB. Some models even propose that dark energy interacts with dark matter in ways that break the universe's assumed symmetry, creating a preferred direction for cosmic structures to form. Then there's the quantum twist. If the vacuum energy behind dark energy fluctuated anisotropically, meaning it wasn't the same in all directions during the universe's birth, those irregularities might have frozen into the fabric of spacetime, imprinting the CMB with their signature. Think of it like a balloon inflating unevenly, with one side stretching faster than the other. The result, a cosmos that's not quite as isotropic as we thought, its earliest moments whispering secrets we're only now deciphering. Critics argue the axis of evil could be a fluke, an artifact of measurement errors or foreground interference from our own galaxy. But the more we study it, the harder it is to dismiss. If dark energy is indeed involved, it would upend our assumption that the universe is fundamentally the same in all directions, forcing us to reconsider everything from inflation to the nature of spacetime itself. Future missions, like the proposed CMB S4 experiment, aim to probe this anomaly with even finer precision, hunting for clues in the polarization patterns of ancient light. What makes this mystery so thrilling is its scope. The axis of evil isn't just a quirk in the data, it's a potential window into dark energy's hidden nature, a clue that the force shaping our universe's fate might be far stranger and far more complex than we ever imagined. Whether it's a cosmic mirage or a revolutionary truth, one thing's certain: the universe is trying to tell us something, and we're just beginning to listen. No force in the universe holds more power over our cosmic destiny than dark energy, yet we still don't know whether its grip will tighten, loosen, or vanish entirely as eons stretch into infinity. This uncertainty isn't just academic, it's the difference between a universe that expands forever into icy oblivion and one that might collapse or tear itself apart. Right now, the evidence points to dark energy behaving like Einstein's cosmological constant, a steady, unchanging presence. But what if it's not? Consider the most straightforward scenario. Dark energy remains constant as it appears to be today. In this future, the acceleration we observe now continues indefinitely, stretching the cosmos into an ever thinner, ever colder expanse. galaxies beyond our local group would eventually vanish beyond an unreachable horizon, their light redshifted into nothingness. Star formation would cease as gas clouds grow too diffuse to collapse. Black holes would evaporate over unimaginable timescales, leaving behind a near-perfect vacuum where even atoms might decay. This big freeze is the default forecast, a slow fade into darkness where time itself loses meaning. But dark energy could be far less predictable. Some theories suggest it might decay over time, its repulsive push weakening until gravity regains dominance. Picture a cosmic pendulum swinging back. After trillions of years, the universe's expansion could reverse, pulling galaxies, stars, and eventually space-time itself back toward a cataclysmic singularity. This big crunch would mirror the Big Bang in reverse, a fiery end where everything is compressed into infinite density. Stranger still, quantum fluctuations in this collapsing universe might spark another Big Bang, birthing a new cosmos in an endless cycle of death and rebirth. Then there's the most violent possibility, phantom energy. If dark energy's strength grows with time, it wouldn't just push galaxies apart, it would amplify its own effect in a runaway feedback loop. The result, a big rip where the fabric of reality is shredded atom by atom. First, galaxy clusters would be torn asunder. Then, stars would explode as the space between their particles expands faster than gravity can hold them together. In the final moments, even atomic nuclei would be split apart, leaving behind a chaotic sea of quarks and radiation. Current measurements can't yet rule out this nightmare scenario. The equation's critical parameter, W, hovers perilously close to the phantom threshold. But the wildest theories go further. Could dark energy interact with dark matter in ways we haven't detected, weaving an invisible web that evolves over cosmic epochs? Might it be tied to the quantum vacuum, its strength fluctuating as space itself undergoes phase transitions? Some models even suggest dark energy could trigger a false vacuum decay, where space-time suddenly collapses into a lower energy state, rewriting the laws of physics in an instant. The truth is, we're peering into the abyss with only flickers of data to guide us. Future missions like the Euclid telescope and the Vera Rubin Observatory will sharpen our vision, measuring dark energy's influence across billions of years. Until then, one haunting question lingers: is the universe's fate already sealed, or are we witnessing just one act in a cosmic drama with twists we can't yet imagine? From the enigma of its origin to the terrifying possibilities of how it might end the universe, dark energy remains one of science's greatest unsolved puzzles. We've explored 25 of its deepest mysteries, why it dominates the cosmos now. Whether it's connected to black holes or hidden dimensions, even the bizarre chance that our entire reality might be a holographic projection. Yet with every answer, new questions emerge. We still don't know if dark energy is constant or evolving, if it's a force, a field, or a flaw in our understanding of gravity itself. We can't say for certain whether the universe will fade into cold silence, collapse in on itself, or be torn apart by dark energy's phantom grip. But that's what makes this era of discovery so thrilling. Every telescope, every experiment, every breakthrough peels back another layer of the cosmic onion, revealing just how much we still have to learn. The James Webb Space Telescope is rewriting our view of the early universe. Euclid and the Vera Rubin Observatory are mapping dark energy's fingerprints across billions of years. Even now, scientists are chasing wild ideas that dark energy might be tied to neutrinos, that it could flicker in and out of extra dimensions, or that its value isn't random but fine-tuned by some deeper law we've yet to uncover. This isn't just a story about dark energy, it's a story about human curiosity, our relentless drive to stare into the unknown and demand answers. And the best part: you're living through it right now. As you watch this, researchers are piecing together clues that could rewrite textbooks. So stay curious, follow the discoveries. Who knows, the next big revelation might come from a telescope not yet built or a theory not yet imagined. If you've made it this far, you're clearly as fascinated by the cosmos as we are. So hit like if you enjoyed this deep dive, subscribe to join us for more journeys into the universe's greatest mysteries, and drop a comment below. What's your boldest dark energy theory? The universe is full of secrets. Let's uncover them together.